So, in the earlier classes we have seen how the current flows in a purely resistive load in an AC/AC converter. Now, let us see what happens when instead of a purely resistive load we have a complex load having resistance and inductance in series. As there is inductance, so the current through this load will not be immediately 0 when the thyristor turns off. It will be continuing to flow even for the some time even after the thyristor stops conducting. So, the voltage and current waveforms, if we plot, then the current will be starting after firing angle alpha, which is the angle at which the thyristor is fired, and it will be even continuing after the thyristor turns off. So, let us find out what will be the current in such a load having inductance in series with the resistance. We will be considering the input voltage to the converter as small v equal to root 2 v sin omega t, where v is the RMS value. Here v is the RMS value of the voltage. So, root 2 into v means peak value is that much. So, it is Vm sin omega t, which is equal to root 2 v sin omega t. Now, if we consider the current in the circuit, so the current in the circuit when one thyristor is firing, say thyristor T1 fires in the positive half cycle at an angle of alpha, then what will be the current that can be found out using Thevenin's voltage law, Kirchhoff's voltage law in this circuit, and that will be giving the law will be giving us the equation which is L di dt, the drop in the resistance plus the drop in the inductance, that will equal to the input voltage. So, writing the Kirchhoff's voltage law, L di dt plus Ri equal to V, which is the input voltage, and that is a sinusoidal voltage. So, root 2 v sin omega t. Now, we have to solve this equation. It is a first order differential equation. So, we know that solving this differential equation will be leading to the current, which is a summation of the complementary function of the particular integral. So, we have two portions in the solution. The complementary function will be given by C is a constant into e to the power minus r by L into t, and the particular integral I p is equal to root 2 v by root over r square plus omega square L square into sin omega t minus phi. So, this is a standard solution I am using instead of solving from the first principle. I am just writing down this equation's solution because it is a first order differential equation. This is the phi is the phase angle which is given by tan phi equal to omega L by r. Now, we need to know the constancy. So, we have to find out this constancy from the first principle, that is initial condition. So, we will be writing the current equation I equal to C into e to the power minus r by L into t plus root 2 v by z. Z is nothing but root over r square plus omega square L square. This is the impedance of the load that is representing the Z, and sin omega t minus phi term, which is the steady state component basically. Now, we will be applying the initial condition to find out the constant C. Applying initial condition means the current in the load will be 0 till the thyristor is triggered, and the thyristor is triggered at omega t equal to alpha. So, we will be using that condition to find out C. So, I will be equal to 0 when omega t is equal to alpha. Putting here the value of omega t is equal to alpha gives us value of t equal to alpha by, here if we replace here C into current is equal to 0 and 0 equal to root 2 b by z sin omega t equal to alpha. So, we will be writing omega t as alpha, alpha minus phi. So, what will be the value of C that can be found out? So, here C is equal to minus root 2 b by z sin alpha minus phi. So, now we can write down the value of I. So, I equal to C is root 2 by v into z sin alpha minus phi into e to the power minus r by L t. So, e to the power minus r by L t plus the other term, which is the steady state component. So, now from this we will be getting the equation for this current I equal to minus root 2 v by z sin alpha minus phi e to the power minus r by L t plus root 2 v by z sin omega t minus phi. So, finally, we get an equation which is giving the value of I, and we can see that the exponential term which is there, because of this exponential term the current in the inductance will be falling very slowly. It is not immediately falling to 0, and depending upon the R and L, the time constant of the inductive circuit, the falling of the current will take place. If it is time constant is high in comparison with the input cycle period, then there will be fall of this current very instantaneously, but if they are not comparable, if the time constant is not so high as compared to the period of the input voltage waveform, then there will be significant lagging of the current, and the current in the inductor will be continuing for a considerable period. We have discussed about the AC to AC converter, and we have seen how control power can be supplied to a load using the AC to AC converter, which employs a thyristor. Now, another application of thyristor is in rectification. So, earlier we have seen rectification in diode circuits. So, diodes were used for rectification, and half wave rectifier, full wave rectifiers we have discussed earlier, but thyristors can also be used for rectification, and here as it is dealing with power, high power, so sometimes it is easier and cheaper to use thyristors in rectification than using other methods, and we will be now discussing about some basic rectifier circuits using thyristors, which will be giving the rectified output, and using half wave rectifier and full wave rectifiers also we can get the rectified output, which basically employ thyristor in the circuit. So, first of all, let us take a simple half wave rectifier using resistive load. So, here instead of the diode which we are using earlier in half wave rectification, we will be having a thyristor, and initially let us assume that the load is purely resistive. So, the input is sinusoidal Vm sin omega t, which is given as the input. Let us take the voltage across the thyristor as Vt, and the resistance has a voltage across it as Vl. We will be trying to find out the waveforms Vt and Vl also in this circuit. So, input is sinusoidal Vs is equal to Vm sin omega t, and we are having a single thyristor firing at an angle of alpha say. So, when the thyristor fires at an angle of alpha, the voltage across the thyristor becomes 0, because that we have assumed in comparison with the voltage at the input. We can assume that the thyristor is having a voltage drop of 0, because the voltage drop is very small and it can be neglected. So, once it is on or in conduction, the thyristor will be having a voltage of 0 across it. Up to the point of conduction, the thyristor is not firing. So, the voltage across the thyristor will be equal to the input voltage, because we can see in this circuit the voltage across this thyristor, when it is not conducting, there is no current flow. So, the voltage which is at the input will be equal to Vt. So, this I am using the symbol Vt and Vl here. So, what will be Vt? Initially it will be equal to the Vs. As soon as it starts conducting, it becomes 0. It will be conducting till pi, because after that the input voltage becomes negative. So, if the input voltage is negative, that means there cannot be any conduction in the thyristor, since the anode is now negative and cathode is positive. This is reversely biased. So, it will not be conducting, and that is why after this pi the thyristor is off, and that is why the voltage across the thyristor is same as the input voltage, and it will be continuing till after this point again alpha angle is exceeded, because alpha is the delay angle. So, after this point again it will have to wait for alpha, and till then the input voltage will be equal to the voltage across the thyristor. Now, what about the voltage across this load resistance? So, up to the point of alpha, that is till the thyristor conducts, the voltage across this resistance RL will be equal to 0. Since no current flows, the thyristor is off, So, the voltage is 0 because the voltage across the resistance equal to current into the resistance. So, it will be 0 till this point. As soon as the thyristor conducts or fires, then what will happen? The voltage across this resistance will be equal to the voltage at the input, because this drop equal to 0, we are assuming thyristor conduction voltage 0. So, this voltage is equal to the voltage across this resistance. So, it will be following this shape of the input voltage, and after the pi phase angle, that will be not conducting, the thyristor will be not conducting. So, the current will be 0, the voltage will be also 0, and again from this point till alpha angle is crossed, the voltage will be continuing to be 0, since there is no current flow in the resistance, the thyristor is not firing. So, the voltage is 0, and once the thyristor fires again in the positive half cycle, after this angle alpha is crossed, then the voltage across the resistance will be again equal to the input voltage. So, these are the waveforms of the voltage across the thyristor and the voltage across the load. Now, we can find out the voltage values, assuming 0 voltage drop across the thyristor when it is switched or fired. We can find out the DC value of the voltage, DC value or average value, because we are having a rectifier, it is a half wave rectifier. So, using the expression for finding out the mean value or the DC value over the whole period 2 pi, we are getting only the output voltage VL within this region only. This is the region where we are having an output voltage in between from 0 to 2 pi. So, from alpha to pi, we are having an output voltage. So, the integration in the expression from alpha to pi will be, rest is Vm sin theta, because the output waveform is exactly following the input waveform Vm sin theta. So, this integration Vm sin theta d theta between alpha to pi has to be done, but multiplied by 1 by 2 pi, because we are having the input voltage between 0 to 2 pi, if we consider output voltage will be between this portion only, and the rest is 0 in the whole period. So, in order to find out the DC value or mean value, we will be using this expression, and that is equal to Vm by 2 pi, constant part can be taken out, integration sin theta d theta will give minus cos theta between the limits alpha and pi, which is equal to Vm by 2 pi minus cos theta. If we put the limit, it will be minus cos pi minus cos alpha. Cos pi is minus 1 minus cos alpha, so 1 plus cos alpha. So, Vm by 2 pi 1 plus cos alpha, this is the DC value of the voltage for this resistive load. Similarly, if we want to find out the current IDC, by dividing the VDC by RL, we will be easily getting the DC value of the current. So, that is what is done here. IDC equal 1 by 2 pi alpha integration alpha to pi Vm sin theta d theta by RL. RL is the load resistance. and it can be written as Vm by 2 pi RL. Integration sin theta is minus cos theta within the limits alpha to pi. So, putting the limits we get Vm by 2 pi RL 1 plus cos alpha. So, this is just a follow up of the DC value of the voltage, dividing this DC value of the voltage by RL, we get the DC value of the current. And if we want to find out the RMS value of the current, then we have to do it according to the way RMS value is found out. So, square of the RMS value if we take, it will be 1 by 2 pi integration alpha to pi square of this expression Vm square by RL square sin square theta d theta. So, this integration replacing this sin square theta in terms of cos twice theta. So, we will be getting finally the value of RMS square equal to Vm square by 4 pi RL square. Putting the limit, we get pi minus alpha minus sin twice alpha by 2. And if we want to find out the average output power to the load, output power is nothing but IRMS square into RL. Average output power to the load. So, that is obtained as IRMS square we have found out, replacing this expression here and multiplying by RL, that will be causing the square in the denominator of RL to vanish. So, what will be here is Vm square by 4 pi RL into pi minus alpha minus sin twice alpha by 2. Now, this example was using a resistive load. Now, if the load is an inductive one, that means instead of having a pure resistance, we are having an inductance in series with the resistance as the load. What will happen to the half wave rectifier? So, what will happen here is that this inductance will not let the current to stop immediately to 0 once the thyristor turns off, but it will be allowing the current to continue for some more time, because the current cannot immediately become 0 in an inductance. It will be following the exponential curve. So, what we will be getting is that if we plot these waveforms in this circuit, again this Vt and Vl and Vs, if we plot, then if Vs as is same, it is a sinusoidal waveform, and the output voltage across this load, across this inductive load, which is equal to the voltage at the input, but here after the thyristor stops conducting, what will be this voltage? After the thyristor stops conducting, it still there will be current flow for some time. So, that is why even after the thyristor stops conducting after pi, from alpha to pi it will be conducting, but after pi also, if we project this point, after pi also there will be a current flow due to which there will be a voltage available across the load, and that voltage is equal to the input voltage. So, if we look into this waveform of the input voltage, from alpha to pi the thyristor is conducting, it is fired at an angle of alpha, then it will be conducting till pi. After pi, the input voltage waveform becomes negative. That is why the thyristor will be turned off. It should have current 0, but it will be not having current 0, there will be current flowing in the circuit. That is why there will be a voltage available across the load, which is equal to the supply voltage. That is why this is the supply voltage, it will be following the supply voltage, and then only it will become 0. So, till when it will be continuing, the current flow will be continuing, that will be decided by the load. So, the current waveform, if we see from this point, there will be conduction of current. So, current will start flowing, and then after this point till this point also current will be flowing, and it will be becoming 0 at this point. After this becoming 0, it will be continuing to be 0 again till alpha is crossed. So, again the current will be starting to flow, and it will be continuing beyond 0 value of the input voltage, and after some time only the current will become 0. So, we have seen that there is voltage available across the load even after the 0 of the input voltage is crossed to the negative side. So, this is a disadvantage, or actually this is should not happen, because we are having a control half wave rectifier, but here in the negative half also there is voltage available across the load. So, we in order to get rid of this negative voltage in the output, what we can do is that we can use a diode which is known as a flywheel diode, which will prevent the voltage across the load become negative. So, how it does so? Let us consider a circuit. Here, in addition to the thyristor which we were having in the half wave rectifier circuit, we are also having a diode. This is a normal or ordinary diode connected in the circuit. So, basically what does this diode do? Now, let us see and try to understand the behavior of the circuit. We are having an inductive load as it is, a resistance and an inductance in series is the load. The current through this circuit is IL, say, voltage across this load is VL. Now, the thyristor fires at an angle of alpha, that is the delay angle. So, what will happen in the positive half cycle? After the alpha angle is crossed, the thyristor will fire, and it will be flowing, it will be causing the current flow through the load in this direction. This diode is reverse biased, so it will not be conducting in the positive half cycle anyway, and we will be getting an output voltage across this resistance and inductance in series, which is the load, which is VL, that is equal to the supply voltage. So, this is the input voltage waveform Vs, it is Vt, this is VL, these notations are to be corrected. So, when we have non-conduction of the thyristor, input voltage and thyristor voltage are same, because it is not conducting. At this point it starts to conduct, it conducts or fires at this point by using triggering voltage. We are firing the thyristor, and then it turns on, thyristor voltage becomes 0, and that is the reason where the current in this region the thyristor is conducting. The voltage across the resistance will be now equal to the supply voltage. So, VL and Vs are same. Now, what will happen when the supply voltage crosses into the negative half cycle? When it enters the negative half cycle, then in the negative half cycle what will happen, that it is anode is negative, but what will happen to the current through the load? Because you see that when the thyristor conducts, the load current is the thyristor current. Thyristor has a current flow through it, that is say IT, we are naming this current as IT, is the current in the thyristor. Now, when it is in the negative half, let us consider this negative half. So, in the negative half cycle, this diode, it is now forward biased. So, the current will be bypassed through this diode. The diode is conducting. The voltage across this diode is 0. It is also we are assuming as 0 because it is very small, 0.7 volt, it is almost 0. So, the voltage across the load is the voltage across this diode, which is 0. When it is in the negative half cycle, the voltage across this load is 0. But mind it, current flows, but that current will be now bypassed by this diode in this circuit consisting of load and the diode. And the supply will not be allowing any current. That means we do not get the supply current through the thyristor, but we are having a current in the load due to the diode current. That is the difference what that flywheel diode is making, because earlier what we have seen in the inductive load, even when it was in the negative half cycle, the supply was in the negative half cycle, at that time we were getting a voltage across the load which was negative. This is the supply voltage and load voltage is same, and the current was flowing. This is in the negative half cycle was also there was current in the load, but here what we are getting is that there is current flowing in the load, but that current is bypassed by this diode. It will be not flowing to the thyristor. Earlier it was flowing to the thyristor. The current in the load was drawn from the supply. It was flowing through the thyristor and the load even when the voltage was in the negative half. It was going into the negative half cycle because of the current in the inductor not being immediately becoming 0. It was following an exponential behavior. So, that was the difference, but here we have seen in this case use of flywheel diode has stopped the voltage across the load becoming negative as was the earlier case. Now, the voltage is 0, but the current flows in the load. We are getting the current in the load, and that current is not through the thyristor, it is bypassed by this diode. So, here what is happening is that if we consider the load voltage or the voltage across this load, that is when the thyristor was not conducting, it was 0. When it starts conducting, it becomes equal to the supply voltage, but as soon as it enters, as soon as the supply voltage enters the negative region, then the thyristor stops conducting. because why the thyristor, the thyristor stops conducting, and because this anode is positive and anode, and in the negative half cycle the anode is negative, so it will be stopping to conduct, and the voltage across this thyristor will be the voltage which will be obtained across this thyristor will be the voltage across this supply, because if we apply the voltage law here, then the voltage across this is equal to the voltage across this, because this diode drop is 0. So, we get the voltage across the thyristor as the supply voltage till again it starts conducting, then again it will be 0, and the voltage across the load, it will be 0 till the thyristor fires, then it will be equal to the supply voltage. As soon as the supply voltage becomes negative, this voltage across the load will become 0, because it is the diode drop is 0. Again it will be equal to the supply voltage after the thyristor fires. Now, what about the load current? Load current is flowing throughout the period, but this is contributed by two different parts. One is the diode current, which flows when you have the negative half cycle. Say in the negative half cycle, as we know, the current is bypassed through the diode and load current flows due to the current in the diode only, and that is the current here, the diode current, and it is exponentially decaying because it is flowing through the resistance and inductance in series. So, because of this time constant of this load, the current which is contributed by the diode current in a negative half cycle will be falling exponentially, and in the positive half cycle this is due to the thyristor current which is drawn from the supply, but in this portion the current is due to the bypassing of the current by the diode. So, we will be having a current which is rising and falling like this. The rising means it is because thyristor is conducting. So, when conducting, it is flowing through the load and thyristor only, and that is why it will be rising from 0 onwards. So, exactly this value is not going to become 0 because it will be falling exponentially, and we have assumed that the time constant of the load is sufficiently high as compared to the time period of the input voltage. So, under that assumption it will be not falling down to 0, and it will be falling, and again it will be rising like this. So, this rectified output is half wave rectified output, and it is not present during the negative half cycle. That has been achieved by using a flywheel diode, which is bypassing the load current in a negative half cycle. So, if we consider now a full wave rectifier using a center tap transformer. So, as we were discussing earlier using diodes, we were using a center tap transformer. Here also similarly we are using that type of circuit using a center tap transformer and two thyristors. When we have two thyristors, what will happen? Alternately the conduction will be taking place. Also we are having a flywheel diode. So, here we are connecting the diode as we have connected in the half wave rectifier. Here also there is a flywheel diode, and the load is of course an inductive load or a complex load R and L in series. So, the voltages across these thyristors are assumed to be Vt1 and Vt2, and we are applying a sinusoidal voltage Vm sin omega t. So, in the positive half cycle of the input signal, the thyristor which will be conducting is the upper one, because in the positive half cycle of AB we are considering this secondary side of the transformer and we will be analyzing the waveform. Let us consider the voltage across AB. Now, the point A, when it is positive with respect to B, it is a center tap transformer, so it will be like plus and it will be minus. This point is the ground, or center point is the ground. So, in this situation the upper one thyristor, that is T1, will be forward biased, or anode will be positive, and it will be conducting at an angle of alpha, say. Both are identical thyristors, we are assuming conduction angle, delay angle is alpha. So, now when it conducts after an angle of alpha, this current will flow through the load, and the voltage across this load, this voltage will be equal to this V E A. This point is ground. So, we are getting the voltage across this load following the voltage at the input, that means at the secondary side. So, if we consider the voltage VA here and VB here, VA and VB will be just out of phase by 180 degree, and so VA will be like this and VA will be like this. So, they are out of phase by 180 degrees. So, now what will be the output voltage? That will be depending upon the current flowing through it. When the current flows through this load, the voltage across this load will be equal to this VA when this T1 conducts. So, that is happening here. When this T1 conducts after angle of alpha, the voltage across the load will be following this VA. Now, in the negative half cycle, when the VA enters negative half cycle, VB becomes positive, but the conduction will not take place in the lower one thyristor T2 till another angle alpha beyond pi, that is, it will be conducting at pi plus alpha only. So, within this region, that is from pi to pi plus alpha, that when VA enters negative half cycle, what will happen when VA enters negative half cycle? That means now this becomes negative with respect to B. So, this is ground. So, what will happen is that the diode, if we look into the diode D, then this N is negative. That means the N is negative with respect to this P, and this means it is forward biased. So, as soon as this VA enters the negative half cycle, then the diode D will be forward biased. So, the load current which is flowing, IL is the load current, it will be contributed by the diode current only. The current will not flow through this transistor, but we will be having a load current which is contributed because of the diode. Since the diode is forward biased, it will be bypassing that load current in this way, in this fashion. And what will be the output voltage across this load? That will be this voltage will be equal to the diode voltage, and which is equal to 0, this voltage equal to 0. So, in the full wave rectifier here we have seen that during the portion when the VA goes into negative half cycle before pi plus alpha angle, this is pi plus alpha. So, we have the voltage across this load 0, but the current which is flowing in the load, that is almost constant, because here the current which is flowing is the diode current, and when the thyristor T1 was conducting, the current was due to this IT1, that IT1 means the thyristor current which was drawn from the supply, because the current flow was from this point A through this load to this point center or ground, and that current is, we are denoting it by IT1. But when the VA enters into the negative half cycle, the diode conducts, the thyristor T1 is now off, turned off, since anode is negative, and the load current is due to the diode current. And if the R and L, that means the time constant of this circuit is properly chosen, then we will be having almost a constant current like this, although contributed by two different components. Each time we are not getting the same contribution from the same component, but here it is the diode current, here it is the thyristor current, but we will be having almost a constant current. Now, in the other half cycle, that means when VB is in the positive half cycle and after pi plus alpha, then the thyristor T2 will fire. The thyristor T2 will conduct now, because it is positive, anode is positive. So, when this thyristor T2 is conducting, then the load current will flow from positive like this, and it will be conducting, and current will be flowing through the load and it will be entering the ground. So, through the load the current enters or flows in the same direction in both the cases. So, now the current in the load is due to the thyristor T2, that is IT2, and again when it will be entering the negative half cycle, then when it enters this half cycle, negative half cycle, then your VA will be entering the positive half cycle, and when VA is entering positive half cycle, then the diode current will flow, because that can be, if we consider now positive half cycle and it is below this alpha, that means it is below the firing angle, then also the diode current will flow. So, it will be continuing, and what is important here is that it is full wave rectifier, that means we are not getting a negative voltage across the load as we are getting without the flywheel diode, but here during the positive as well as the negative half cycle of each signal, we are getting output waveform across this load, that means we are getting the output voltage across load, and in between the two conduction by the two thyristors the voltage is 0. When the diode is conducting, the diode voltage is 0. So, this is the typically the output voltage waveform for a full wave rectifier using center tap transformer and flywheel diode. So, here we have seen that the rectification using this thyristor, it will be having a output voltage waveform across the load with no negative portion. Similarly, there are also circuits for full wave rectifier using bridge. So, if we consider bridge rectifier, bridge type rectifier using the thyristors, we will be having thyristors. In addition to those thyristors, we will also be using diodes. So, the circuit for a bridge rectifier, of course, we are using single phase bridge rectifier, we are till now considering single phase only, but it can be extended to 3 phase also. So, what will be the shape of the bridge rectifier? It is having diode and thyristor in series like this, we will be having pairs of diode and thyristors, they will be conducting in pairs. So, here this is say D1, this is say T1, this is D2, T2, and the supply is given between A and B, which is a sinusoidal supply Bs. And apart from this diode thyristor pairs, we will be having a single diode connected in this way across this load R and L. So, this is a single phase bridge rectifier circuit. The voltage across this load is VLC. Now, here what will happen, this Vs, when it is in a positive half cycle, we can see that the diode D1 and the transistor D2 will conduct. In the positive half cycle, this diode D1 and T2 will conduct. So, these pair will conduct, and in the negative half cycle, when this is negative, in the negative half cycle, that means it is like this, then we are having the diode D2 and T1 conduct. So, in pairs they will be conducting and the current will be flowing through the load after firing of the thyristor, because only after firing of this thyristor T2, this loop will be complete and the current flow through this load will be occurring. And when it is conducting, when this thyristor say T2 is conducting in a positive half cycle, the voltage across this load VL, if we consider, if this is the input voltage Vs, then if we draw the voltage VL, that is the voltage across this load. Here say alpha is the angle and pi, this is again alpha, pi plus alpha, and this is 2 pi like this. And so, the VL will be following the input voltage like this, and from here to here it will be the other pair will be conducting and we will be getting the voltage like this. So, we will be getting this output voltage, the rectified output voltage, but the difference between this earlier rectifier using center tap transformer and this bridge rectifier is that we are having pair of diode and thyristor which will be conducting one pair in 1/2 cycle, and this is the diode which is there to prevent the output voltage to become negative. So, today we have seen the application of the thyristor in rectification. We have studied about the half wave and full wave rectifier, and we have also seen for an inductive load how the flow of current in the load takes place for the presence of a diode, and how the voltage across the load which goes negative when the thyristor does not stop conduction can be prevented by using a flywheel diode. So, using a flywheel diode we have seen that the voltage across the load is stopped from going down to negative values, and we get proper rectified output across the load. So, the thyristor in this way is used in many of the applications which are useful in power control.